point, we have our basic antiderivative rules. We have the reverse power rule. We can use the reverse power rule for definite and indefinite. We have our rules for antiderivatives of trig functions. So you know how to find the antiderivative of all the basic trig functions. We've now looked at the antiderivative of e and ln x. So just like we have a mean value theorem for derivatives, and we have our average value, which is like our slope of the secant, these same properties and same areas come into play with antiderivatives. So what we're going to do today is talk about an average value of a function as well as the mean value of a function with definite integrals. So the average value Now I won't echo. So the average value of a function says, suppose that you wanted to take the average temperature during a 24-hour period. So how could you do it? Well, let's suppose that you take the temperature at time t on each hour from midnight to midnight. Once you start to measure those temperatures at equally spaced times, then the average temperature becomes the number of temperatures taken divided by or the sum of the temperatures taken divided by the total number of temperatures you took. So if I take the temperature 12 times, then I divide by 12. If I take it 24 times, then I divide by 24. And that would give me the average temperature over a period of time. So in calc, what we do is think of average temperature kind of like a Riemann sum. So if you think about taking larger measurements, that's like making larger rectangles. That would make the time, or the delta t, equal to 24 divided by n. Or we can say that our n subintervals is equal to 24 over delta t. Delta t represents the width of the time, so that's the width of times of the temperatures we took. So if it was every hour, then delta t is 1. If it was every half hour, then delta t is 0.5. If it's every 2 hours, then delta t is 2. So delta t can kind of be factored out because that would represent your width. And then when you would sum up all of your times, etc. And then you divide that by your total number. And we could think of this as a Riemann sum because this would represent the height of the triangles at their widths, but now the difference is this n value. So that's kind of like a constant, so you could factor that out in front. So that would kind of be like 1 over n, and then the summation of all these values. So starting with I equals 1, going up through n, and then it's f of t sub I
mine over.
And then your delta t. So it's 1 over the number times f of t sub I times delta t. So this part right here represents the Riemann sum. This represents the average of the Riemann sum. So the 1 over the n is going to give you that average. So in the case of this example, if we want average temperature over a 24-hour time period, that's kind of like the integral from 0 to 24 of f of t dt. So that would be the sum of all the temperatures in the 24-hour time period. And if I wanted to find its average, then I would divide that by 24. Or we know you can factor out a constant, so it's kind of like 1 over 24 from 0 to 24 of f of t dt. And that average, or that 1 over 24, we're going to see where that 24 comes from with respect to our problem and our bounds in a second here. Okay. So the average value of a function is simply a summation of all of the values and then averaging them up. As a talking point, it says, do you think that at any point during the day, the temperature reading on the thermometer would be the exact value of the average temperature? So again, what that means is we know temperature is constant. So if the day begins at midnight and it's 32 degrees, as the day progresses, temperature typically increases. So it usually meets its max around the afternoon. And then as the day continues, it starts to decrease. So if that's time 24 and this is time 0, and those are all your times in between, if the average temperature is, let's say, 36 degrees, then, well, that's good for it. Then will the average temperature ever equal? The answer is yes. In order for the average temperature to occur, at some point during the day, since temperature is constant, meaning that it is continuous, it is changing at little tiny increments, the average temperature would have to equal the actual temperature at some point during the day. And in my example, if I got the average temp was 36, then it occurred twice. So the average isn't the max occurs somewhere else. It's just asking, can this occur? And the answer is yes. So what type of problem does that remind you of? To remind you of a derivative type problem. Let's talk about what? Yeah, it's like MVT, right? MVT said slope of the secant equals slope of the tan. This says that the value of the integral equals the average value of the integral. So average area equals actual area. So by definition, the average value formula is 1 over b minus a. So remember I told you we'd find out how to find that n value. It's represented by b minus a, because that's your upper minus your lower. So that should make sense, the beginning to the end of your interval. So I feel like the average value of an integral is very logical. It makes sense how you get it. Think about how you find averages back in the day. You sum up all the totals divided by the number of totals. Well, here in this equation, we sum up all the area divided by the length of the area to give me the average area. So it says find the average value for the function f of x equals 4 minus x squared. So that represents a quadratic reflected and shifted up 4 units. So that's a quadratic that's shifted up 4 units. It's open down because of the negative. And I should know that the properties of a quadratic, so it goes, if there's no stretching or compressing, it goes down 1, right 1, down 4, right 2, because it's the perfect squares. So we're going out to 3. So what that means is this is going down 9 and over 3. So my quadratic goes to the point 3, negative 5. It has the point 2, 0, and it has the point 1, 3, as well as the point 0, 4. So again, you can almost see all your perfect squares in there, but being shifted up 4. So it'd be like negative 9 plus 4, negative 4 plus 4, so on and so forth. So it says find the average value of f of x. So we know how to now do a indefinite or definite integral. So the average value would be 1 minus 3 over 0, because it's b minus a. The integral from 0 to 3. And then our function is 4 minus x squared dx. So that's simply a power rule. So that's 1/3 4x minus x cubed all over 3 being evaluated from 3 to 0. So once you take your antiderivative, the dx goes away. When you take your antiderivative, the bounds go from the summation symbol to the n. So those are just little tiny things you have to make sure. They're kind of like the limit. Once you took the limit went away. Once you take the antiderivative, the dx goes away. So you get 1/3, plugging in 3. So you have 4 times 3 minus 3 cubed, which is 27, divided by 3. Minus 4 times 0, and then that negative would technically distribute, so you'd get 0 cubed over 3, but we know anything times 0 or 0 divided by anything is 0. So you get 4 times 3, which is 12, 27 divided by 3, which is 9, 12 minus 9, which is 3, so you get 3 times a third, which means that the average value of this function, 3 times a third is not 3, 3 times a third is 1. So the average value of this function, which we would say AVG of f of x, is equal to 1. the average value of the function is equal to 1. It doesn't ask me, though, for the average value. It asks me to determine, does the function take on the average value? So just like for MVT, what we did was say, okay, what is the slope of the secant? Does the derivative equal the slope of the secant? So in this case, what is the average value? Does the function ever equal the average value? So we're going to set 4 minus x squared equal to 1. So we get x equals plus or minus the square root of 3. Now we know that the negative square root is outside my interval. So that negative square root's outside that interval. So the answer is yes at positive root 3. The average value will equal the actual value. So yes, at root 3, the average will equal the actual. Okay? So this is essentially, like we said, the mean value theorem. The mean value theorem for integrals says that if you are finding the area under the curve from A to B, that there exists some number C such that the area has to equal the area under the curve for that rectangle. So again, the integral from A to B of f of x dx represents the area from A to B. The area of the rectangle is the height at C, and then the width of B minus A. So our average value function, f of C, is derived from that type of idea, where f of C stands for the average value, is equal to 1 over b minus a in the integral from a to b of f of x dx. So every time we do something new, it's kind of helpful to see where it is derived from. So this is a direct relation to where did this come from, and kind of like why does it look the way it looks. So it comes from the idea that it's the area of the shaded region, the area of the rectangle, and then combining them together to find its average. So just like in derivatives, you said f prime of c equals the slope of the secant. For integrals, it's f of c equals the average value of the integral. So the formal definition for mean value theorem says if f is continuous on the interval, not integral, sorry, that's hard to understand. If f is continuous on the interval a to b, then there exists a point C in that closed interval such that f of c, which is the original, will equal the average value of the integral. So the original equals the average value of the integral. because you have an example my notes didn't have. Sorry about that. Well, the one's an add-on question to it, but I'll go back to it. I must have accidentally deleted the project. I just skipped it. No. Okay, so are you good now then? Okay. So your example 2 is actually my example 4 on this same piece of paper. So I think I probably meant to like delete example 2 off of where it is because I moved into example 4. But for whatever reason your notes packets didn't save, but my PowerPoint did. So sorry about that. So you don't have to worry about that example 2 in the notes packet because it's example 4 coming up in my slides. So before we look at a crazy function like x minus 1 squared, where we don't have a chain rule yet, we're going to actually look at how we can do this on the graphing calculator. So go ahead and take out your graphing calculator. You're going to use NINT, which is feature number 9 in math. And you're going to find the average value, and then we're going to talk about how to find it by hand. So again, just making sure we can use those graphing calculators. Go ahead, and what you're going to do is on your calculator, you would have to do in front of the integral, you would type in your fraction, so that's hitting that second, and then the alpha key, and y equals, so you can get your fraction. Let me get out my camera. There you go. So what you would do on that graphing calculator is go in and you would hit second and clear out everything on there so you can be on a nice clean page. This calculator got busted, that's why I use it back here so you guys don't ever have the bad ones. And then what you do is you hit alpha y equals. That gets you the fraction key on the calculator. So for your fraction, I would type in the 1/3. Get out of the fraction. Then go to math. Go down to option number 9. Type in your integral lower than upper. Type in your function. So make sure you do x minus 1 in parentheses squared. Fill in your variable x at the end and hit enter. So we see that the average value of this function is 1. So then what you could do if this was a graphing calculator, if it was, the values would probably be grosser. But what you would want to do at that point then is go to your y equals, type in 1 for y1, and then type in the function for y2. Because when 1 is equal to the function, that would give you your intersection. So there's my y equals 1. There's my function. Now again, if I wanted, I could have changed my window so that it only went from 0 to like 4. Because you don't want to get tricked into thinking that the function equals the average value outside of the givens. So this went from 0 to 3. So what you'll notice is you can go down to intersect. You can move your cursor along the first line, so in this case my blue. hit enter, move it along the red, hit enter a third time, and we see that the graphs intersect at 2, 1. Now my screen, because it's all glitched out, is hard to see, so I'm just going to move my X window so you can see it better. But, the way it's off the glitchy part, you can see that these graphs also intersect over here. You would want to check to see if that intersection is also in your interval. So you get close to it, and we see that they also intersect at 0, 1. Since it's a closed interval, 0 is included. Therefore, it is a second point at which the average value assumes the function value, or the function assumes the average. So at 2 and 0. Now this problem's pretty easy, so this would definitely be a case in which you would not have a graphic calculator. So let's look at this case where we do this problem by hand. So f of c, or the average value, is equal to the integral from a to b of my function divided by the upper minus the lower bounds to give me the average. So it's 1/3. Take the inverse power rule, but the only way to take the inverse power rule is to have FOILed x minus 1 squared, because we don't have a chain rule for integration yet. So that's x squared minus 2x plus 1. So the power rule gives me x cubed over 3 minus 2x squared over 2 plus x. Now no plus c because this has bounds. So 3 to 0. Cancel those 2's. So you get 1/3. Plug in your 3, so you have 3 cubed over 3 minus 3 squared plus 3 minus zeros, because 0, 0, 0. 3 cubed is 27. 27 divided by 3 is 9. Minus 9. So that cancels. Plus 3. So we do in fact see that we can also calculate that average value of 0. Of 1. And then you set your average value equal to your function. And this is kind of like a completing the square problem. So what you're going to do is square root both sides. When you square root both sides, then what you have to do is make sure you don't lose out on the plus or minus for the square root of 1. So it's plus or minus the square root of 1 equals x minus 1. So then you have your two roots. You have x minus 1 equals positive 1, and x minus 1 equals negative 1. Which gave x equals 2 and x equals 0. So we see that we have the same ones we got from the graph. So that example 2 that we had previously skipped is my example 4 on this next coming slide. So what that represents is a semicircle shifted up and reflected. So you don't have to go back to your example 2. I retyped it here. So it said find the average value of the function on the interval without integrating by appealing to the geometry of that region. Because again, we don't have a reverse power rule for a square root. because there's function composition happening and we don't have a function composition. So for this example, you have to take into account that this represents a circle of radius 1, shifted up 1, and reflected. So that means that its vertex of the circle is at the origin, at -1 and +1, it'll be at its heights of 1. Because again, if you plug in -1 squared is 1, 1 minus 1 is 0, square root of 0 is 0. So you get 1 minus 0, which is 1. And if you plugged in 0, 1 minus 0 squared 0, 1 square root of 1 is 1, 1 minus 1 is 0. So you can see kind of where that graph is coming from. So remember that the value of the integral represents the area of the integral between the curve and the x-axis. So this is not a triangular region because this is a curve. So what we have to do is actually find the area of the rectangle and subtract the area of the circle so we can get the area of the darker shading. So in order to find this function value, we need the area, the area of the rectangle so its base is 2, its height is 1, so its area is 2. The area of a circle is pi r squared. Well, in this case, my radius is 1, and it's only half of the circle, so we divide that by 2. So the area of the rectangle minus the area of the circle gives the area of the dark shading. So it's equal to 2 minus pi halves. So that area of that shading, its average would then be that 2 minus pi halves. So that represents the integral from -1 to 1 of f of t dt. So we say that's equal to 2 minus pi halves. So its average would be 1 over b minus a times that value. So that'd be like 1 over 2. So 2 times a half is 1, and a half times a half is a fourth. So that would mean that the average value is like 1 minus pi fourths. So it said find the average value of the function's integral by using geometry. So there's my average value of the function using geometry. So everything we've talked about in 5.1, 5.2, 5.3 is all sort of coming back to me in 5.4. 5.5 is trap roll. So we're really starting to close in on finishing out chapter 5. The last thing we have is fundamental theorem, which we'll look at tomorrow. So let's look at just that last page and make a summary of everything we've said. So, and this is kind of even a bigger summary. F of x is the antiderivative of f of x if f prime x equals f of x. So f of x is the antiderivative if f prime x equals f of x. See, I didn't want it to but so, for example, if you had f of x equals x squared, its antiderivative is f of x equals 2x. What was down at the bottom was actually fundamental theorem that we're going to talk about tomorrow. Based on my thoughts, I wanted to flip-flop the orders because of the connections we were making this year, first year's past. So then the last thing is just these examples with average values. So, and making sure we haven't totally forgot all of our rules. So yesterday we did a lot of indefinite. Today there's some definite. So the antiderivative of cosine is sine. And then you evaluate from pi halves to 0. So that's like sine of pi halves minus sine of 0. So you have to really know your trig values. So the sine of 0 is 0, sine of pi halves is 1. 1 minus 0 is 1. That second example is just your power rule.
And please report to the office.
So again, you add 1, divide by your new 1, so you get x cubed being evaluated from 2 to negative 1. And then it's always upper minus lower. So we get 8 minus a negative 1, which becomes 9. And you can cross out C, because again, that is an inverse trig function. And I am waiting to see or hear at our next NIMSY meeting what they've done with inverse trig in terms of the AP test this year. Because it was not on it last year. So I gotta get an update for this year. But again, inverse means that this is the unit circle value, and you have to find the value with which it occurs. So if you actually work that out, again, that's our basically the derivative of the inverse sign backwards. And then the idea of inverses, which you do have to know and understand because they do happen with derivatives, is that the inverse sign of 1/2 becomes its unit circle radian value. So this part over here you do need, which is why I finished out the problem, because that is part of derivatives that we did talk about. So I have just a couple textbook problems from you because our textbook doesn't have a ton. And then I have some AP problems for you. So you have the next kind of like 40 minutes to work on these, ask me questions, go through, and then we'll go through our test too. But I'm going to get quick you started on his quiz that he owes me. And let you guys get started on this. If you want to take your break now, you can have your 4 minutes till 21. There's the textbook, and I'll put the worksheets on your desk.